Now that you know just a tiny little bit about hyperbolic functions, how to differentiate them, and also a little bit about their interpretation, we can move to the next rule of differentiation, what I would call the rule to rule them all, the rule that you'll probably be using the most throughout your degree. That's chain rule. The rules we've covered so far allow you to differentiate a lot of functions. You no longer need to do it from first principles, and you've actually seen the proofs. Those rules really do work. However, in practical terms, they are not enough to deal with a lot of functions that become much more complicated. One of the important reasons why that is the case is because functions can be much more complicated than just being quotients, products, or sums. And specifically, they can be what we call functions of functions, or even functions of functions of functions of functions of functions of functions of functions. You get the point, right? For those functions, we'll need to use chain rule. But before we go there, let's define what we mean by a function of a function or a composite function. Composite functions are those where you can't just plug in a value and you get something directly out. For those functions, you'll be plugging something that gives you an output, and that output still needs to be processed by something else before you get the result. Now, a function like this will describe the displacement of a pendulum from equilibrium with an amplitude of A and a phase phi. Even if you ignore the physical interpretation and focus on the maths, you can see why this can be considered a function of a function. If you want to measure this displacement x of the pendulum or something else, you need to know the time. If you know the time, you can plug it in, but what happens is before you get x out, you need to process this term first. In a way, you can say that this is a function of time and that the overall displacement is a function of time. It means that this is a composite function, something where first you need to process one function and then you give it to another function, in this case sine, you multiply it by a before you get the final result. There are two main things that you can do to test whether you're dealing with a composite function or a simple function. One is to look at the function and try to read it and understand whether you can calculate or get the output directly. For example, let's say that you have some function and you give the function some x value. If you get a y value directly out, that typically means that you have a simple function. A composite function will look different and you need to read it off, or maybe think about how you would input it into the calculator, where parentheses will be crucial. A composite function will look at least as complex as you input x to, say, function 1. This gives you an output, let's say z, and then this output is given to be processed by a second function, and then you finally get your y out. Composite functions can be as complex as you want, which means this process could keep going to function 3, 4, 5, 6, 7, 8, 9. But there's nothing like testing your understanding and seeing whether we're in the presence of a composite function or not. We've cleared the board, so we now have space to test some functions. Let's have a look at candidate number 1. I present you candidate number 1. Is this a composite function or a simple function? This is quite an easy example. You can have a look at the brackets, and also you can see how this would be processed. It's clearly a composite function. There's a function here that we could call f of x. Once we process this value, we give this to the log, which is another function that we could call g of f of x. And after the log is processed, the value is given to the sign and processed again. So we could say that this is h of g of f of x. In this case, we're in the presence of a composite function. So candidate number 1 is a composite function. Let's bring candidate number 2. Now this candidate is a little bit more modest, but let's take a proper look at it. Can we just input x and get something out? Yes, we can. This is very simply a function of x. We can process it and we don't need to give it to anything else, which implies that in this case we are not in the presence of a composite function. This is a simple function, which is great because it's incredibly easy to differentiate. Now let's get rid of this and bring candidate number 3. Candidate number 3 is interesting. Is it really a composite function or not? It turns out that if you think about it, it is. You still need to process this, which means that when you plug in x, you square it, you get a value, and then you give it to ln of that value, and then you get it back. In this case, candidate number 3 is a composite function. Now, what about candidate number 4? This is quite an interesting one. We've had a look at x squared plus something that we can calculate directly. In this case, if you think carefully, you cannot process it in one go. First of all, we need to process this part, and then we need to square it. So the entire function could be defined as g of f of x. So this means that candidate number 4 is a composite function. Now let's get a trap for you. Let's change candidate number 4 to candidate number 5 by doing something tiny, like this. All we did was change the exponent, the power that we're taking the function. We're still processing it first and then processing it again. This is quite a tricky one. Technically, by writing it like this, you're actually writing it as a composite function. But what is happening is, once you process f of x, then you won't really be doing anything to the output. It's the same as kind of be multiplying by 1 or adding 0, but you're still doing something. This is therefore kind of a trap that technically I would say this is a composite function, although it is also the same as just writing x to the power of 2 plus 1, and in this form technically it is a simple function. Maybe you should look out for cases like this for the Kahoot. Just saying. Something quite important though is to understand that if you have some function that's g of f of x, in general this is not the same as having f of g of x. In other words, for a composite function, the order matters. And this is why it's so crucial the way you type things into a calculator or a computer program and you close a parenthesis. Expressions are essentially processed inside out, and changing the order will change the results. So keep this in mind, and I think now we are ready to introduce or revise chain rule.